Okay, we're going to run through this one fairly quickly because there's not an awful lot to it, but we've looked at first principles, and I suppose I've said you have to know how to do it by first principles. It's important that you know how to do it, but it's not how we would really do it. And what we will be using is this general rule or this power rule. And this is kind of how it's laid out here. So if I have a function which is x to the power of something or anything to the power of something, what we do is we multiply by the power and we reduce the power by 1. We take away 1 from the power. So we can see here where it was x to the power of n, we multiply by n so that n ends up in front, and the power then becomes n minus 1. We've reduced it by 1, we make it 1 smaller. So looking at how that works for these different examples here, if I have y equal to x squared, dy dx is going to be 2x to the power of 2 minus 1, which of course is just 2x. Same thing goes for f dash x here. Multiply by the power, so 2 multiplied by 3 gives me 6. I reduce this by 1, so I get 6x squared. For the last one, it's going to be ds dt, because t is my variable, and that just gives me 4. Okay, the other key thing to note here, I suppose, with my derivatives in following it this way is, say for the last example there, when I reduce that power by 1, I get t to the power of 0, so that's just 1. If I have no variable at all, so say I'm finding the derivative of just, say y is just equal to 7, then dy dx is just going to be 0. The derivative of a constant just goes straight to 0. If we have more than one term, say like we have here, we just do them one at a time, following through in the same way. So here dy dx would be 4x plus 3. For this next one, f dash x is 18x squared minus x. 18x squared minus x. So multiply with the power, reduce the power by 1. And the last example here, then dv dh is 4h plus 1. So it's important that you're kind of fluent with these ideas. Multiply by the power, reduce the power by 1. And the other key things there, as I said, is if it's a constant term and we differentiate it, we just get 0. The other thing I would say with these ones is it's important that you're used to your indice rules. So knowing, for example, that the square root of x is the same as x to the power of a half means that we can do the derivative using this rule. Otherwise, we would find that a little bit harder. I suppose the last thing we can have here is just that extra step of maybe finding the derivative at a particular point. So say I calculate my derivative here, I might want to know what the value is when x is minus 2. And that gives me 6 times minus 2 minus 2, which is minus 12, minus 2, which is minus 14. So I've found a general formula for the derivative or for the slope, and then I find it at a particular point by substituting in. So in the exam questions here, these ones, fairly straightforward. They generally lead to further steps. There generally is more to these questions, and we'll use this idea when we're looking at some of the more complicated rules, but it's an important one to have off. Let's just start by rewriting this function here. X squared is perfect. 1 over x we should know is the same as x to the power of minus 1. That's from our indice rules. And by doing that, we can now use this general rule, multiply by the power, reduce the power by 1, it becomes minus 2, and I get 2x plus 1 over x squared. Okay, so it's really important that you know your indice rules as well. Looking at this 2004 question, I can find the derivative fairly easily. 3x squared plus 12x plus 15. The 36 just goes to 0 when I differentiate it, because a constant, when it's differentiated, just becomes 0. And the second part here says show that it can be written in this form. We should recognize, hopefully, this form as completed square. So it's completed square form. So to do that, let's rewrite my function. So 3x squared, I have to factor out my 3 first. X squared plus 4x plus 5. Okay, so I get x squared plus 4x plus 5. I need to add in, I divide the middle term by 2, I square it, that gives me 4. So I add in 4, and I'm also going to subtract 4, because I can't just change the question for no reason. But what I can do is that enables me then to write it in a perfect square form. So I'm going to move the 4 over here, and I'm going to keep my plus 5 minus 4. So this is all completed square. This is back in algebra 2. So x plus 2 squared plus 1. And we've rewritten it in the format they wanted, with the 3 staying on the outside there. But the general idea still applies. It's a very, very important rule for you to know. It's very important that you know this general rule so that you know how to get the derivative of a general power. So just multiply by the power, reduce the power by 1, and then also remembering that the derivative of a constant, so the derivative of a constant is just going to be equal to 0. Very important as well. So if we have a constant term and we do the derivative, that's just going to be 0. And think about what that would mean. If we have y equal to 4, it makes sense then that if the derivative is related to the slope there, that the slope would just be 0 at that point. But yes, an important rule for you to have off, a nice short one for us to go through, but just an important rule for you to understand and to be able to apply, I suppose, in terms of your differentiation. And we will be looking more at the applications and what it all means in a general sense. But as we've said, derivative generally gives us the slope of the tangent, so we can use this power rule to quickly find that. It may depend on the value of x, and if it does, then we may need to substitute in different values of x for different points in the function. And just remembering that the derivative of a constant will just give me 0.